We're traveling to the past so you can relax and benefit from this experience. Don't forget to show your support and appreciate the material, as by the end of our conversation, you'll feel comfortable and at ease. Close your eyes and let's begin the story. In the vast reaches of space, filled with stars, billions of planets spin, some of which might host life different from our own. Some of these worlds are submerged in immense oceans, where unusual organisms could be lurking on the ocean floor, while others are hidden beneath icy crusts, holding mysterious waters that could sustain tiny life forms, feeding on chemicals from the depths. There are planets that strikingly resemble Earth, with soft starlight, gentle clouds, and conditions that give hope for the existence of advanced extraterrestrial life. Special devices explore the solar system, while telescopes capture the light of distant worlds. Each new piece of information sparks hope for significant discoveries. For centuries, humanity has sought to determine if we're alone in the boundless expanse of the galaxy. Astronomers examine stars in search of new planets, and engineers design devices capable of exploring the surfaces of other worlds. Writers create captivating stories about encounters with unknown beings, while scientists analyze molecules found in space. Just the faintest clues, like radio waves, traces of gas, or fragments of organic matter, can ignite interest. The universe is silent, but this silence inspires the creation of new tools to capture signals from space. The search for life covers numerous directions. The red planet, dotted with craters and canyons, contains traces of conditions that could have supported life billions of years ago. The moons of Jupiter and Saturn, covered in ice, hide oceans beneath, where simple organisms could thrive using energy from the depths. The planets orbiting distant stars discovered in recent decades amaze us with their similarities to Earth, and their atmospheres may contain gases indicating the possibility of advanced life. Research doesn't stop at bacteria capable of surviving extreme conditions. It also includes civilizations that might transmit signals across the galaxy. Scientifically, life represents chemical processes that evolve, adapt, and pass on characteristics to the next generation. This concept opens up the possibility for numerous hypotheses. Life could exist in subglacial seas, where minerals and heat trigger chemical reactions. It might thrive in methane oceans with completely different structures than those on Earth. Or perhaps it flourishes in the clouds of planets with unique chemistry, governed by different laws. Each hypothesis adds new shades to the cosmic picture. Diverse approaches help us inch closer to the answers. Rovers on Mars gather samples that could reveal the planet's past when its climate was more hospitable. Probes investigate moons whose depths beckon with signs of biological activity. Telescopes capture the light of distant worlds to identify gases linked to life. Methane in Mars' atmosphere, organic molecules from geysers of moons, and water vapor in the atmospheres of other planets. Each discovery, like a mosaic piece, deepens our understanding of the universe. This search combines precision of measurements with bold curiosity that drives discoveries. Now, let's explore what conditions are necessary for life among the stars. Before starting our journey through space in search of life, it's crucial to understand which factors must be present for life to arise and develop. Science long believed that life was only possible with certain chemical components and favorable external conditions. Today, we realize that life possesses an incredible ability to adapt and diversify, but there are still three main criteria scientists pay special attention to. The first and most important condition is the presence of liquid water. This relates to its unique physical and chemical properties. Water can dissolve many substances, fostering interactions between various chemical elements and compounds. It's also the medium in which molecules can move freely and engage in chemical reactions. Without the ability to exchange substances and energy, it's hard to imagine the emergence and development of living organisms. On Earth, Liquid water covers a vast portion of the planet's surface and is a key requirement for life. It can exist in other states, like beneath ice or deep below the surfaces of planets and their moons, but the liquid form is considered the most promising for the emergence and sustenance of life. The second important component is carbon. Carbon has unique chemical reactivity. Its atoms can bond with one another to form long and stable chains or rings that serve as the foundation for complex organic molecules. These compounds are the building blocks of living cells, allowing the creation of diverse molecular structures necessary for information storage, metabolism, and executing complex biochemical functions. Carbon is the optimal element for forming a stable and diverse biology similar to Earth's. The third condition for the existence of life is a source of energy. Without a continuous supply of energy, a living system can't maintain metabolism, grow, or reproduce. On Earth, the primary source of energy is the sun, where plants capture sunlight and convert it into chemical energy used by other organisms. However, life can also exist in complete absence of sunlight, deriving energy in other ways. A vivid example of such conditions on our planet is the deep-sea hydrothermal vents, known as black smokers. They're located at significant depths in the oceans where sunlight cannot reach. Here, hot solutions saturated with minerals and chemicals are expelled from the Earth's depths under high pressure. Around these underwater sources, entire ecosystems form, where bacteria derive energy not from light, but through chemical reactions, such as the oxidation of hydrogen sulfide and other compounds. These bacteria become food for more complex organisms, like worms, mollusks, crabs, and even deep-sea fish. However, even with all three components, water, carbon, and energy, there's another crucial condition known as the habitable zone. This is the region around a star where temperatures are mild enough for liquid water to exist on a planet's surface. Sometimes it's referred to as the Goldilocks zone, similar to the well-known fairy tale where the heroine chose porridge that was neither too hot nor too cold, but just right. Our planet is located in the center of such a zone, one astronomical unit from the Sun. Because of this, Earth enjoys a temperate climate and vast oceans, creating ideal conditions for life. The boundaries of the habitable zone depend on the type of star, its temperature, and size. For instance, for small red dwarfs, the habitable zone is much closer to the star than for hot blue giants, where it's significantly farther away. A striking example of the importance of the habitable zone is Mars, which today lies on its edge and has lost much of its surface water, even though conditions might have once been much more hospitable. Sour lakes and complete darkness of deep caves. On our planet, such beings are called extremophiles and serve as an excellent example of life's remarkable ability to adapt to almost any conditions provided by nature. It's these extremophiles that inspire scientists to search for life in the most unusual and hard-to-reach corners of space. To effectively search for life in various habitability indices in the universe, astronomers had to develop specialized systems that determine how suitable a planet is for the emergence and maintenance of life. Currently, two such index systems are actively used, helping to assess the potential of planets and highlight the most intriguing candidates for detailed study. The first of these systems is called the Earth Similarity Index. This index considers three key parameters of a planet: its mass, radius, and surface temperature. Evaluation is conducted on a scale from 0 to 1, with Earth taken as the standard, having a maximum value of 1. The closer a planet's index is to 1, the more its characteristics resemble Earth's, and the higher the likelihood that life, as we know it, could exist there. A planet's mass plays a fundamental role since it determines gravitational strength. If gravity is too strong, the planet retains a heavy, dense atmosphere, making life development difficult. Conversely, If the mass is too small, the planet quickly loses its atmosphere, adversely affecting the stability of its surface conditions. The radius of a planet influences the internal structure and composition of its core, which in turn governs vital processes like plate tectonics and the magnetic field that protects the surface from radiation. Surface temperature is a key factor for the presence of liquid water and the possibility of biochemical reactions, which are fundamental to any known form of life. Planets with a high Earth similarity index, usually between 80% and 100%, immediately attract astronomers' attention, since this indicates conditions on such worlds are very close to Earth's, increasing the likelihood of life. Such planets may have oceans, moderate temperatures, and an atmosphere similar to Earth's, making them prime targets in various scientific missions. However, limiting searches to exact copies of Earth would be a mistake. Nature can create entirely different forms of life in unexpected conditions, prompting the development of another system, the Planetary Habitability Index. Unlike the first index, it considers the possibility of life existing not only under familiar conditions, but also based on completely different chemical foundations. This approach allows researchers to speculate about organisms in worlds that initially seem extremely inhospitable. The Planetary Habitability Index takes into account potential life forms that could utilize alternative chemical compounds and habitats. For instance, it examines conditions where, instead of water, other liquids like methane, ammonia, or hydrogen sulfide play a key role. These environments may not support life as we know it, yet they might sustain entirely different hypothetical types of organisms. The index also considers diverse potential energy sources that could support biological processes, including not just sunlight, but also chemical energy resulting from reactions between various substances in the atmosphere or the planet's interior. Moreover, this evaluation system even accounts for possible differences in the biochemistry of organisms, which might not use carbon as their primary structural unit. Using both indices in conjunction allows for the creation of a broad and flexible assessment system, enabling researchers to prioritize studying not only worlds that closely resemble Earth, but also planets that significantly differ from familiar conditions, yet still possess potential for life's emergence and evolution. This comprehensive approach greatly increases the chances of significant scientific discoveries and helps us understand how diverse life might be in the universe. Until recently, scientists believed that life could only develop under Earth-like conditions, with moderate temperatures, liquid water availability, and low radiation. However, research over the last few decades has significantly expanded our understanding of possible conditions for life's existence. Organisms capable of surviving in extremely harsh conditions, previously deemed entirely uninhabitable, have been discovered on Earth. These findings have generated alternative hypotheses, suggesting that life in the universe could be much more diverse than we previously assumed. One of the most intriguing hypotheses is the idea of life existing in methane oceans. While methane is unsuitable as a solvent and even toxic for terrestrial organisms, it can serve as water under different conditions. At low temperatures found on some celestial bodies, methane becomes a liquid, forming lakes and seas. In such methane bodies, organisms with entirely different biochemistries could develop, utilizing compounds dissolved in liquid methane, similarly to how terrestrial organisms use compounds in water. A striking example of such conditions is Saturn's moon, which has large lakes and seas of liquid methane, regularly replenished by methane rain. In such an environment, hypothetical life could use methane not only as a solvent, but also as the basis for its metabolism, forming a completely new and currently unknown biochemical structure. Another intriguing hypothesis considers silicon as a potential alternative to carbon for creating organic life. Carbon is a unique element forming the basis of life on Earth, capable of forming long and stable chains and diverse complex compounds. Silicon, being the closest analog to carbon in chemical properties, could theoretically also form chain structures and compounds that might be used to create analogs of organic molecules. However, silicon is more chemically inert and more frequently forms solid, insoluble compounds like quartz and other minerals. Despite these limitations, under high temperatures or entirely different chemical environments, like hot planets with volcanic activity, silicon-based life could theoretically find a way to exist. While this remains purely a hypothetical scenario today, scientists seriously consider it as a potential direction for searching for life in extreme conditions on other planets. Another important hypothesis concerns the possibility of life existing under conditions of extremely high radiation. On Earth, radiation is considered a serious factor limiting organism survival, yet some bacteria and archaea demonstrate incredible resistance to radiation exposure. For instance, a bacterium known as Deinococcus radiodurans can survive in radiation levels thousands of times greater than lethal doses for humans. Organisms adapted to such conditions. Organisms capable of surviving in high radiation environments might inhabit space, on planets with thin atmospheres, or on the moons of giant planets where radiation exposure significantly exceeds that of Earth. These creatures protect their genetic. The planet had a much different climate. Evidence suggests it had a thicker atmosphere and liquid water on its surface. This could have supported various forms of life. Researchers believe conditions might have been suitable for microbial life. The remnants of ancient riverbeds, deltas, and dried lakes tell us about this wetter past. Furthermore, rocks containing clay minerals only form in the presence of water, reinforcing this idea. In polar regions, extensive deposits of water ice exist. Ice can be found in craters and beneath thin layers of dust, especially at mid-latitudes. Seasonal phenomena on the Martian surface also intrigue scientists. During warm periods, dark streaks appear on crater slopes, known as recurring slope lineae. These formations occur in the same locations and vanish when temperatures drop. Initially, researchers thought these might result from liquid saline water seeping through. However, later studies indicated temperatures in those areas are too low for stable liquid water. The most accepted explanation now involves dry flows of dust and sand across salty deposits. Despite this, the question of potential life on Mars remains unresolved. The nature of the processes happening on the planet is still unclear. Methane emissions, detected by both orbiters and ground measurements, spark particular interest. Methane levels fluctuate throughout the year, peaking in summer and decreasing in winter. This seasonal variability is noteworthy because on Earth, much methane is produced by microorganisms. However, geological processes are also considered, such as water interacting with specific rock types, which could generate methane. There are hypotheses suggesting that gas might accumulate in underground cavities and periodically escape through cracks in the crust. The mechanism behind methane's formation remains undetermined, and its origin is the subject of ongoing research. The data collected indicates that Mars had completely different climatic conditions in the distant past. According to current models, around 4 billion years ago, the planet had a denser atmosphere, higher temperatures, and stable bodies of water on its surface. Traces of ancient riverbeds, deltas, and lake deposits confirm that water could exist in liquid form for long geological epochs. These conditions fostered the development of stable ecosystems at the microscopic level. At some point, Mars lost a significant portion of its atmosphere, leading to the inability to retain heat and liquid water. The main cause of this process is thought to be the planet's weak magnetic field. Unlike Earth, which has an active core and a powerful magnetic field protecting its atmosphere from solar wind, Mars lost its internal geodynamics early in its development. This allowed charged particles from the Sun to gradually blow the atmosphere into space. Although the process occurred slowly, it was relentless. When atmospheric density dropped to a critical level, the greenhouse effect weakened, temperatures decreased, and water first turned to ice before partially evaporating. The loss of atmosphere made the planet vulnerable to radiation, and its climate became dry and unstable. The early period of Mars' history is considered the most promising for potential life. With water, energy sources, and necessary chemical elements, the possibility for simple organisms could have arisen. If life did emerge on Mars during a milder climate with flowing water, it might have shifted to subsurface layers as conditions worsened. These areas offered relative temperature stability and protection from radiation, especially after the atmospheric barrier was lost. In such protected zones, microscopic organisms capable of feeding on chemical reactions in rocks or near possible underground heat sources could survive. Current research missions, like the rover sent to a crater that once contained a lake, aim to explore such regions. Since early 2020, this rover has been studying a crater that was once a standing body of water. This area was chosen deliberately, as deposits formed in the delta could preserve organic molecules and microscopic structures for billions of years. The rover not only examines the region's geology, but also collects Martian soil and rock samples in sealed containers, which are planned for future return to Earth. The sample return project is scheduled for the 2030s. Its goal is the first ever laboratory analysis of Martian materials using modern organic and isotopic chemistry techniques. This approach will accurately determine if the samples contain traces of ancient biological activity. Besides the Mars mission, one country has initiated the first comprehensive interplanetary mission with an orbital apparatus and landing platform. Since early 2021, this rover has been operating in the plains, studying geological features, conducting soil spectral analysis, and photographing the surrounding area. Although this mission doesn't include sample return, it also aims to clarify conditions that may have existed in the past and expand mapping data. Scientists focus on searching for signs of ancient life and assessing the chances of its possible preservation in subsurface layers. Both directions share the aim of answering a vital question. Could Mars, in its early history, have been a planet where life developed alongside Earth? Research continues, and each new sample, measurement, or photograph of the surface brings us closer to a deeper understanding of this ancient planet. While Mars is depicted as cold and dry, Venus is a completely opposite world, shrouded in heat and high pressure. Modern Venus is considered one of the most inhospitable planets in the solar system. Its surface temperature reaches 460 degrees, high enough to melt lead. Atmospheric pressure on Venus is about 90 times greater than on Earth, equivalent to the pressure at a depth of 1 kilometer underwater. Additionally, the planet's atmosphere is filled with thick clouds saturated with sulfuric acid, blocking visible light and creating a powerful greenhouse effect. This appearance of Venus is hardly associated with life. However, recent research data gradually shifts our understanding of its past. According to climate models developed by scientists 2 to 3 billion years ago, Venus may have looked different. It's hypothesized that oceans of liquid water might have existed on its surface during that time, with temperatures and atmospheric composition much more favorable, similar to Earth's conditions. The planet's climate was likely maintained by a cloud cover that reflected solar radiation and a stable water cycle that could have persisted for hundreds of millions of years. Under such conditions, Venus could have been potentially habitable, at least until the moment of a sudden greenhouse collapse, transitioning the planet into a state of thermal runaway. The reasons for this transformation are not fully understood. It's believed that the evaporation of oceans and accumulation of carbon dioxide in the atmosphere led to an uncontrollable enhancement of the greenhouse effect, causing a sharp temperature increase and complete evaporation of water. One main argument for the idea that Venus once had a significant amount of water is the ratio of heavy hydrogen to regular hydrogen. On Venus, this ratio greatly exceeds that of Earth. This indicates that light hydrogen from water molecules evaporated into space, while the heavier isotope remained. After the breakdown of water molecules, hydrogen was swept away by the solar wind, as the planet lacks an effective magnetic field. Due to its extremely slow rotation, Venus's magnetic field is about 100,000 times weaker than Earth's and cannot protect its atmosphere from solar wind effects. The atmosphere likely interacted with rocks and sulfur compounds, and to a lesser extent, it could have leaked into space. As a result of these processes, a dense and dry atmosphere, rich in carbon dioxide, formed, featuring acidic clouds and an absence of a water layer. These changes rendered the surface of Venus completely uninhabitable. However, research isn't limited to the planet's surface. In 2020, a group of scientists reported the discovery of phosphine gas in Venus' atmosphere, a substance typically associated with biological processes on Earth. Phosphine can form from the activities of anaerobic microorganisms. This discovery sparked active scientific discussions. Although the data faced criticism later and measurement methods were revised, the mere fact of the discussion opened new horizons for research. Some scientists suggest that stable zones might exist in the upper atmosphere, where temperature and pressure are significantly lower than on the surface, where life capable of adapting to acidic environments could survive. If they exist, microscopic organisms could be present in aerosol droplets, obtaining nutrients from the planet's gaseous envelope. New research missions, such as Da Vinci and Veritas, aim to gather more accurate information about Venus's past and assess its habitability during early geological epochs. The first will study the chemical composition of the atmosphere and conduct scans. On the way to the surface, scientists aim to refine our understanding of the greenhouse effect and uncover signs of water vapor and favorable conditions in the past. The second mission will focus on the planet's geological structure. By utilizing radar mapping, it will help clarify the tectonic and volcanic processes that might have played a key role in the climate catastrophe. Modern Venus remains a world of extremes, but its past and potential signs of habitability make it a main target for studying climate changes on planets and the fate of Earth-like worlds. After examining our nearest planets, it's time to shift focus to the more distant worlds of the solar system, such as the giant planets Jupiter and Saturn. Their moons initially appear cold and lifeless, covered in ice and lacking an atmosphere. However, beneath this frozen crust, oceans are hidden. Liquid water persists due to internal heating caused by tidal friction. These worlds, obscured from view and devoid of light, could be promising candidates for primitive life. The focus is on Jupiter's moon, Europa, and Saturn's moon, Enceladus. Europa is considered one of the most likely candidates for hosting life among Jupiter's moons. Despite having a smaller diameter than Earth's moon, it conceals a vast subsurface ocean beneath its icy shell, with a volume greater than all of Earth's oceans combined. The ice layer varies in thickness from 10 to 30 kilometers, with estimates suggesting a liquid water layer beneath it that could reach depths of up to 100 kilometers. This water world doesn't freeze due to tidal heating caused by Jupiter's gravitational pull, which compresses and stretches the moon's interior, converting mechanical energy into heat. Europa's surface is crisscrossed by a network of cracks and lines, forming a complex geometric pattern. These formations indicate the mobility of ice and its interaction with the liquid water beneath. In some areas, there are so-called chaotic regions, where the ice appears cracked and mixed. These areas could serve as sites where the subsurface ocean erodes the crust from below, pushing fragments to the surface. Such regions are particularly interesting as they may preserve a chemical link between the ocean and the surface. In the late 1990s, a spacecraft studying the Jupiter system provided crucial data. It recorded magnetic disturbances indicating a layer of electrically conductive fluid, likely salty water. Additionally, spectroscopic data revealed the presence of salts and sulfur-containing compounds on the ice surface. These substances probably erupted from the ocean through cracks in the crust. While no organic traces were found, the mere possibility of chemical exchange between the ocean and surface makes Europa especially appealing for further searches for biomarkers. Beneath Europa's surface, at the bottom of the hidden ocean, hydrothermal vents similar to those found in Earth's oceans may exist. These vents form when water interacts with heated rocks and serve as the foundation for ecosystems independent of sunlight. On Earth, such conditions host bacteria and archaea that utilize chemosynthesis to convert chemical energy into organic matter. These organisms form stable communities that support food chains in complete darkness. Such conditions, at least theoretically, could sustain life in Europa's ocean. To test these hypotheses, the Europa Clipper mission is being developed, set to launch soon. The spacecraft is expected to arrive in the Jupiter system in the early 2030s and conduct numerous low-altitude flybys over Europa's surface. It will be equipped with spectrometers, radar, and particle analyzers capable of detecting biomarkers and analyzing the ice structure. Special attention will be given to areas where recent material ejections from the ocean might have occurred. If organic molecules or unusual isotopic ratios are found on the surface, it would provide strong evidence for life beneath the ice. While Europa may require drilling through kilometers of ice, Enceladus, Saturn's moon, actively ejects samples of its internal ocean into open space. It's one of the most astonishing objects ever explored in the solar system. Its diameter is about 500 kilometers, and even at this modest size, it displays incredible activity. Powerful geysers have been discovered at the South Pole, ejecting jets of water, vapor, salts, methane, ammonia, and microscopic ice particles into space. These jets burst from cracks in the icy crust called tiger stripes. Observations by the Cassini spacecraft over 13 years revealed that the plumes contain organic compounds, including complex carbon-based molecules. It was also determined that the composition of these geysers indicates water's contact with a rocky seafloor, which is a necessary condition for chemical reactions, similar to those that nourish microbes on Earth. Such processes include reactions between water and minerals that release hydrogen and methane. These substances could serve as an energy source for microscopic organisms akin to Earth's methanogens. On Earth, methanogenesis is considered one of the oldest metabolic pathways, and its presence on Enceladus, combined with other substances, makes the hypothesis of life quite plausible. Scientists emphasize that even if methane forms non-biologically, the conditions under which it arises still represent a favorable environment for a potential biosphere. Various options for returning to Enceladus are currently being discussed. One proposal involves a life detection mission that would fly through the geyser plumes, collecting samples directly from them. Studying the jets containing complex organic molecules, proteins, and other possible life indicators allows for data collection without landing on the icy surface. This enables direct analysis of substances emerging from the ocean. Although exact timelines for implementing this idea are still undetermined, this concept appears promising for astrobiology in the coming decades. Titan, Saturn's largest moon, also captures scientists' attention. It's larger than Mercury and boasts a unique atmosphere, with surface pressure nearly 1.5 times that of Earth. Titan is the only place outside our planet where liquid is consistently present on the surface, though it's not water. It's methane and ethane. Rain falls here, rivers and lakes form, and coastlines develop, all made of hydrocarbons. These conditions create a unique environment, making Titan the first celestial body where a complete liquid cycle, similar to Earth's, was discovered, but based on light organic compounds. The Moon is shrouded in a dense orange haze, where complex photochemistry occurs in the upper atmosphere due to solar radiation and particles from Saturn's magnetic field, forming diverse organic compounds. The Cassini-Huygens mission conducted in 2005 allowed for greater understanding of Titan. The Huygens probe landed on its surface for the first time, transmitting images of plains dotted with rounded icy pebbles and data on the atmosphere and upper soil composition. Organic materials were found, settled from the atmosphere, indicating the presence of chemical building blocks necessary for life. Titan might host alternative forms of life based on liquid methane rather than water. Surface temperatures reach around 180 degrees, making water hard as stone. However, methane remains liquid, acting as a solvent. On Earth, all living organisms rely on water, but Titan could harbor organisms with different structures that utilize methane reactions, surviving extreme cold. These concepts are still hypotheses, explored within astrobiology, chemistry, and theoretical biophysics. For further exploration, NASA plans the Dragonfly mission, set to launch in 2027, with arrival expected in 2034. Unlike past missions, Dragonfly won't be an orbital spacecraft or rover. It'll be a flying drone capable of traveling significant distances through the air. Titan is the only body in the solar system where a dense atmosphere and low gravity allow for such a concept. The drone will land, take off, and move between interesting locations, investigating various geological and chemical zones. The mission's primary objectives include analyzing organic compounds, studying the surface, searching for signs of past or potential life, and identifying conditions for a biogenic synthesis of complex molecules. Dragonfly will be the first mobile astrobiological survey on another world. If Titan truly contains elements that enhance our understanding of alternative life forms, this mission will mark a significant milestone in space exploration. Detection methods for exoplanets are evolving. One reliable approach is the transit method, which observes a star's brightness dip when a planet obscures its light. This is the technique used by a famous telescope that helped discover thousands of new planets. It's particularly effective for large surveys, tracking many stars simultaneously. Another method involves radial velocities, which record star oscillations caused by a planet's gravitational influence. Even if a planet is invisible, its effect on the star's movement can be observed. This method confirms a planet's existence and measures its mass. Other techniques exist, such as direct observation, where powerful telescopes capture infrared light emitted by exoplanets against the backdrop of a star. This happens only in rare cases, especially for massive, young and hot gas giants far from their stars. Modern astronomical advancements now allow for real images of such exoplanets, like those in the HR 879 system, where 4 planets were detected moving. These images don't provide surface details, but show the planet as a glowing dot near the star. In recent years, a new telescope has played an essential role in observing exoplanets, analyzing light spectra passing through a distant planet's atmosphere during transit. Scientists search for water vapor, methane, carbon dioxide, and other potential biomarkers in these atmospheres. These measurements require high precision and can take months, but they help detect planets and assess their similarity to Earth. The discovery of exoplanets has transformed our view of the galaxy. What once seemed an exception now appears potentially common. The question of how many of these worlds could support life remains open. However, the more we learn, the less unique Earth seems. Among numerous exoplanets, those with high Earth Similarity Index ratings, accounting for mass, radius, temperature, and other parameters, attract special interest. The closer this index is to 1, the more similar the conditions are to those on our planet, though this doesn't guarantee habitability. Nonetheless, such planets are particularly intriguing for future study. One such world is Kepler 438b. Discovered by the Kepler telescope, it quickly captured researchers' attention. Its index is about 0.88, making it one of the most Earth-like exoplanets. It belongs to the class of super-Earths and is a rocky planet slightly larger and more massive than Earth. The radius of Kepler 438b is roughly 12% greater than Earth's, and its mass ranges from 1 to 2 times that of Earth. However, the exact value isn't determined yet, as direct measurements remain impossible. The planet orbits the star Kepler 438, located about 470 light-years from Earth. The star in the constellation Lyra is a red dwarf, which are cold and low-mass stars. Its mass is about half that of the Sun, with luminosity just a few percent of solar output. This suggests the habitable zone around it is much closer than in our solar system. Kepler 438b completes a full orbit around its star in 35 Earth days, falling within the hypothesized region where liquid water could exist on the surface. However, this system has serious features that question the possibility of life on the planet. Like many stars of this type, Kepler 438 is an extremely active red dwarf. Observations show it frequently produces powerful flares and radiation bursts, potentially tens or hundreds of times more intense than the most severe solar storms. Over 2 years, such flares were recorded approximately every 20 days, with some energy levels significant enough to impact the nearby planet. With such stellar activity, the planet's atmosphere, if it ever existed, could have undergone substantial degradation. In the absence of a protective magnetic field, the atmosphere could gradually dissipate under the influence of charged particle streams. If the planet lacks its own magnetic field like Earth, this might mean its surface is exposed to radiation, disrupting conditions for a stable biosphere. Conversely, if a magnetosphere exists, it could protect the atmosphere and create more stable conditions. However, this hypothesis remains untested. We lack data on whether the planet has a magnetic field or not. Interestingly, orbital parameters indicate a high likelihood of tidal capture, meaning one side of the planet always faces the star, while the other remains in constant shadow. Such conditions might create thermal imbalances between hemispheres, but if the atmosphere is dense enough, it could mitigate this contrast and distribute heat. Currently, it's unknown whether Kepler 438b has an atmosphere, what its composition is, or if it has any moons. These data can only be obtained with more precise equipment in future missions. Research missions, like next-generation telescopes capable of conducting transit light spectroscopy. Currently, the planet remains theoretically one of the most promising candidates, but with an important clarification. A high degree of similarity doesn't automatically mean high habitability. Kepler 438b serves as an example of how a combination of encouraging characteristics and a harsh stellar environment creates a complex picture. Such planets expand our understanding of the possibility of life and prompt a re-evaluation of the role of stars in the fate of potentially habitable worlds. Now, let's move to another star system, located about 40 light-years from Earth. This is the TRAPPIST-1 system, home to several rocky planets that have long captured astronomers' attention. Interest in it arises not only from its proximity, but also from its unique compact structure. 7 exoplanets orbit the star, and at least 3 of them lie within the estimated habitable zone. One of these planets is TRAPPIST-1e. It ranks among the exoplanets with a high Earth Similarity Index, around 5, making it one of the most intriguing for astrobiology. Its mass is about 0.7 times that of Earth, and its radius is around 90%. The planet's density is nearly identical to Earth's, indicating a rocky structure with a metallic core. TRAPPIST-1e sits in the habitable zone of its star, where temperatures may allow for liquid water on the surface. It completes an orbit around the star in 6 Earth days, suggesting a close orbital distance. The entire TRAPPIST-1 system is so compact that the orbits of all 7 planets fit within Mercury's orbit. This creates a dynamic environment with resonances and gravitational interactions between the planets, aiding in more accurate determinations of their masses and densities. The star TRAPPIST-1 is an ultra-cool red dwarf with a temperature of about 2,500 degrees Celsius. It's 10 times lighter than the Sun and emits only a fraction of a percent of sunlight. Most of its radiation falls in the infrared range, causing energy reaching the planet to distribute differently than on Earth. However, the overall thermal load meets conditions where water could exist in liquid form if an atmosphere is present. TRAPPIST-1e likely experiences tidal locking, meaning one side always faces the star, while the other remains forever in shadow. Nevertheless, climate models show that with a dense atmosphere, temperature differences could smooth out through efficient heat transfer. This creates a possibility for a stable strip of temperate climate along the line between light and dark. Little is known about the potential atmosphere of the planet. Initial observations with modern telescopes show no signs of a dense water envelope, reducing the likelihood of greenhouse overheating and making it even more intriguing. The hypothesis of an atmosphere composed of nitrogen with added carbon dioxide or other inert gases remains. If TRAPPIST-1 indeed has a stable atmosphere and liquid water exists on its surface, even partially, one wonders what forms of life might thrive in such unusual conditions. The planet primarily receives infrared radiation, and if the biosphere uses photosynthesis, it might rely on pigments sensitive to long wavelength light. Hypothetical organisms could have dark colors, black, purple, or brownish red, to capture as much available energy as possible. The gravitational force on TRAPPIST-1e is slightly lower than Earth's, so potential life, especially multicellular, might be more elongated and lighter. If the climate is stable and atmospheric pressure isn't too high, advanced terrestrial ecosystems adapted to low light and high humidity could develop. On the sunlit side, organisms resilient to constant radiation and capable of energy storage could dominate, while on the dark side, beings might rely on chemosynthesis and heat. The skin color of living beings could vary depending on the environment. On the sunny side, it'd likely be dark to enhance light absorption, while on the shadowy side, it might be light or translucent if organisms utilize bioluminescence or infrared vision. Such asymmetry could even be observed within a single organism living in the transition zone between light and dark. The TRAPPIST-1 exoplanet is one of the most studied and promising. Its proximity to Earth, the stability of its star, rocky structure, and potential atmosphere make it a priority for astrobiological research. Among exoplanets resembling Earth but located farther away, Kepler 452b stands out. This planet earned the unofficial title Older Sister of Earth due to its similar characteristics and orbit close to Earth's. However, its star system is significantly older, and the planet itself is larger, heavier, and has a longer history. Kepler 452b orbits the star Kepler 452, approximately 1,400 light-years away in the direction of the constellation Cygnus. This star belongs to the same spectral class as the Sun, but is about 10% brighter and 500 million years older. This makes it an important object for studying the evolution of planetary systems similar to ours but at later stages of development. Kepler 452b is a super-Earth and is estimated to have a radius about 60% larger than our planet. Its mass can't be measured directly, but based on the assumed density, it could be 5 times heavier than Earth. These parameters suggest a high likelihood of a rocky structure, although more massive atmospheres or water ice impurities in the mantle can't be ruled out. The Earth Similarity Index for Kepler 452b is approximately 0.83, making it one of the most Earth-like among distant objects discovered. It lies within the habitable zone and orbits at a distance comparable to Earth's, with a year lasting about 385 days. This orbital stability under moderate stellar radiation creates favorable thermal conditions. The temperature on the planet's surface can resemble Earth's if it has a dense atmosphere and a developed greenhouse effect. However, the system's age has a dual effect. On one hand, over more than 6 billion years, stable geological and climatic processes may have developed on the planet. On the other hand, prolonged exposure to stellar radiation, especially in the early stages, could have led to atmospheric loss if the planet lacked a magnetic field or sufficient gravity to retain it. Therefore, the question of Kepler 452b's habitability remains open. Another hurdle for study is its significant distance. It is much farther away than, for example, TRAPPIST-1, making it difficult to study with the same level of detail. Modern telescopes can't analyze the atmosphere or confirm the surface composition. However, the existence of such an object, similar to Earth and on a mature orbit, suggests that Earth-like planets might be common around stars like our Sun. If Kepler 452b does have a stable atmosphere and liquid water, life could have evolved under higher pressure and gravity than on Earth. Organisms on its surface might be more compact and stronger, adapted to high gravity and potential temperature fluctuations. A more mature system allows for the possibility that if life did arise there, it could have gone through complex evolutionary stages. This exoplanet marks a significant milestone in the search for planets beyond our system. It was the first Earth-like object discovered orbiting a Sun-like star within the habitable zone. Although it's too far for the nearest missions and studies, it played a crucial role in understanding that our planet isn't unique in its characteristics. Similar worlds could be scattered throughout the galaxy. Once an exoplanet is found, the next important task is studying its atmosphere. The gas composition may contain vital information, such as the presence of water vapor, oxygen, methane, ozone, and other molecules that could indicate biological or geochemical processes. These components, particularly in specific combinations, are considered potential biosignatures that point to the existence of life. Since exoplanets are too distant to observe directly, scientists use the transit spectroscopy method. This approach involves observing how a star's light passes through a planet's atmosphere as it crosses the star's disk. When a planet transits in front of its star, some of the light filters through the atmosphere, and various gases absorb light at specific wavelengths. This creates a spectroscopic fingerprint that helps determine the atmospheric composition. High-sensitivity telescopes are needed to detect even minor changes in radiation flow. One primary tool became a space telescope launched in late 2021. It operates in the infrared range, making it ideal for analyzing cold stars and planets. In its first few years of operation, the telescope began collecting spectra of the atmospheres of some exoplanets, mainly gas giants, but the method is gradually adapting to smaller rocky worlds. Among the early successes were the detection of water vapor, carbon dioxide, hydrogen sulfide, and methane in the atmospheres of hot exoplanets. While this doesn't confirm the presence of life, the data shows that the technique works and allows for increasingly accurate chemical composition analysis. As more data accumulates, conclusions about temperature, pressure, cloud structure, and even possible climate circulation on the planet's surface will emerge. However, the method has serious limitations. First, It only applies to planets that transit their star from the observer's perspective, which is a small fraction of all known systems. Second, the signal itself is very weak. Even under ideal conditions, the light passing through an exoplanet's atmosphere is only a fraction of a percent of the total flow. If the star is active, like most red dwarfs, flares, magnetic storms, and spots can distort or mask the signal, complicating analysis. Additional difficulties arise from distance. The farther a system is, the weaker the signal, and the more time is needed for observations. Even with long exposures, data remains noisy and requires complex computer processing. Moreover, modern telescopes struggle to accurately study the thin atmosphere of Earth-like planets, especially those orbiting bright yellow or white stars, whose light vastly overwhelms the faint signal from the planet. Despite this, progress in spectroscopy continues. New methods are being developed, including direct separation of the light spectrum from the planet and the star, as well as coronagraphs and star shades that can block the star's light and study the planet in isolation. In the coming decades, new telescopes such as LUVOIR and HABEX are planned to conduct detailed analyses of the atmospheres of Earth-like planets, even at significant distances. The question of whether other intelligent beings exist remains one of the most intriguing and important in science. If life, especially in microscopic forms, could be widespread throughout the universe, then the emergence of intelligence is a more complex and rare process. That's why specific programs aim not at finding biological traces, but at identifying signs of technological activity. The most well-known initiative focuses on the search for extraterrestrial intelligence. This program aims to detect narrowband radio signals that can't be produced by natural sources. In most cases, objects in nature emit across a wide range of frequencies, while artificial signals like those from radio or television have very narrow bands. Detecting such a signal from the search for extraterrestrial intelligence with a clear frequency structure could confirm the existence of a technological civilization. For these purposes, radio telescopes are used to capture the faintest oscillations in the radio range. One traditional band for searching is around 1420 MHz, corresponding to the hydrogen atom's emission frequency. This choice isn't random, as hydrogen is the most abundant element in the universe, and an intelligent civilization could use its universality to transmit signals. The most famous event in the history of the search for extraterrestrial intelligence remains the so-called WOW signal, detected in 1977. It was discovered by radio astronomer Jerry R. Ehman. During a standard sky survey, the telescope recorded a narrowband radio signal lasting 72 seconds, exactly what the antenna's configuration allowed for observing one patch of sky. The signal was so powerful and clear that Ehman, impressed by what he saw on the printout, wrote "Wow" in the margins. That's how it got its name. The signal met all criteria for artificial origin. It was in the right range, had a specific shape, stable frequency, and abruptly stopped when leaving the reception zone. However, all subsequent attempts to detect it again were unsuccessful. It remains the only unconfirmed episode. Neither natural sources nor terrestrial interference have been definitively identified as its cause. In recent years, a hypothesis emerged that the signal might have been caused by an astrophysical event, such as a star flare or magnetar interacting with a cloud of cold hydrogen. Such a combination could have amplified radiation at the hydrogen line frequency and created a burst resembling this signal. However, this version hasn't received definitive confirmation, and the signal remains one of the most mysterious episodes in the search for extraterrestrial intelligence. There were also more trivial cases of observations. For many years, the observatory in Australia recorded mysterious pulses that remained unexplained for a long time. It turned out that these signals occurred when staff opened the microwave door located near the antenna. The resulting pulses entered the telescope's reception area and were registered as potential anomalous signals. This case became a classic example of how even household appliances can trigger false alarms in radio observations. Nevertheless, the observations continue. Increasingly sensitive receivers, automated algorithms, artificial intelligence, and data processing on supercomputers are being employed. New telescopes and antennas cover more stars and frequency ranges. The search for extraterrestrial intelligence has long transcended individual telescopes, evolving into a distributed observation system involving institutions worldwide. In 2015, the most ambitious extraterrestrial intelligence project to date was launched. It was initiated as part of a program and received financial support of $100 million over 10 years. The main goal is to systematically scan 1 million nearby stars and several hundred nearest galaxies for artificial radio signals, optical pulses, and other potential signs of technological activity. Observations are conducted using the largest radio telescopes, including observatories in America and Australia. The project's equipment allows simultaneous monitoring of millions of frequency channels, covering a broad spectrum with high precision. In addition to radio observations, the project also searches for laser pulses in the optical range, which could serve as an alternative form of interstellar communication. A key feature of this project is the use of artificial intelligence to analyze vast amounts of data. Machine learning algorithms help filter radio interference, search for anomalous signals, and detect statistical deviations from background radiation. As a result, over 2.5 million observational sessions have been analyzed. Although the project hasn't yet recorded a confirmed signal from extraterrestrial civilization, it has found some unusual signals that caught the scientific community's attention. One of the most discussed cases is the signal designated as BLC-1, detected in 2019 toward Proxima Centauri, the closest star to the Sun. The signal was narrowband, stable, and did not match known sources of radio interference. Initially, it sparked significant interest, as it came from a region of the sky where an exoplanet with potentially habitable conditions exists. However, further analysis suggested the source was likely anthropogenic, meaning it was linked to human activity. Researchers concluded that it was probably a complex combination of terrestrial radio interference coinciding in time and frequency with the observation direction. Nonetheless, the need for such deep analysis highlighted the importance of using automated and critically tuned approaches in data processing. In addition to BLC-1, the project periodically records isolated signals that lack obvious explanations but cannot be reliably verified. These cases remind us of the complexities involved in the search. A signal might be genuine but one-time, or it could arise from a combination of poorly understood technical factors, creating the appearance of an anomaly. This project isn't just an attempt to catch an extraterrestrial transmission. It's a systematic, large-scale, and technologically advanced program that lays the groundwork for future research, enhances radio observation methods, standardizes analysis algorithms, and trains a new generation of researchers. Even if no signal from extraterrestrial intelligence is ever recorded, this work is already expanding the technical and theoretical horizons of radio astronomy. While most projects focus on searching for radio signals, there's another avenue, attempting to find indirect traces of technological activity not related to message transmission. This idea is based on the assumption that a highly advanced civilization with considerable resources and time might leave behind technical constructions or energy signatures noticeable over interstellar distances. Such approaches are grouped under the term search for technological signatures. One of the most well-known hypotheses in this area remains the Dyson sphere concept, or megastructure, hypothetically. The devised megastructure concept around a star aims for maximum energy efficiency. Proposed by physicist Freeman Dyson, it suggests that an advanced civilization could extract energy from a star more efficiently than humanity does. A complete shell or network of solar panels surrounding a star could absorb most of its radiation and re-emit it in the infrared range. Thus, one way to detect such a structure is to look for signs of thermal anomalies, where a star emits less visible light than expected while producing excess infrared. Research on such objects has observed stars with unusual brightness variations. The most famous example is Tabby's star, whose brightness periodically dropped to 20% without an understandable cause. This sparked numerous discussions, including the hypothesis of partial shading by some megastructure. It later became clear that such dimming was likely related to clouds of dust or large comets, but this case laid the groundwork for further systematic searches for similar anomalies. Another direction of research became the analysis of optical signals. While radio communication is an energy-efficient way to transmit information over vast distances, laser pulses could represent brief yet bright signals detectable over interstellar distances. Modern ground-based telescopes can detect nanosecond laser flashes if they are bright enough or repeated. Active attempts are underway in one research program to systematically monitor nearby stars in the optical range for such pulses. Astronomers actively employ artificial intelligence and machine learning methods to process vast data volumes. Contemporary algorithms can handle billions of signals, identify deviations from statistical norms, filter out false alarms, and highlight anomalies that might go unnoticed by humans. Such systems are already being implemented in various projects, and their importance will only grow in the future. Despite extensive efforts to find signals, no convincing evidence of intelligent extraterrestrial civilizations has yet emerged. This contradiction between the high theoretical likelihood of life in the universe and the lack of concrete data embodies the so-called Fermi paradox. Formulated in the mid-20th century, it poses a simple question. If intelligent life forms are widespread, why haven't we detected any signals or traces of their presence? Preliminary estimates suggest there could be over 100 billion stars in our Milky Way galaxy, with a significant number hosting planetary systems. If even a small fraction of these planets lies in the habitable zone and life develops on one of thousands of them, intelligent beings should arise multiple times in various locations. Yet, searches for radio signals and technological traces have yet to yield positive results. One possible explanation for the paradox is the assumption that intelligent life is extremely rare. While microscopic life can emerge with energy and water, developing intelligence involves many complex evolutionary steps. These include the emergence of multicellular organisms, sexual reproduction, nervous systems, language, culture, and technological thinking. Each of these stages may be so unlikely that humanity turns out to be the only representative in the galaxy. In this scenario, we could be unique because similar processes either haven't started yet or have stalled. Other hypotheses suggest that advanced civilizations might not seek contact. This concept is known as the dark forest hypothesis, which posits that intelligent species recognize the risks of interacting with other life forms and prefer to remain silent to avoid potential threats. Like a hunter in a dense forest, every being tries not to attract attention, as any display could lead to danger. In this case, there could be many intelligent beings, but they all hide, and we, as novices in this forest, don't yet realize the dangers of loud communication. Another commonly discussed explanation is that the technological stage of civilizations is very brief. Technological development inevitably leads to the creation of tools capable of destroying their creators. This can manifest as global wars, ecological disasters, biosphere destruction, loss of social stability, or uncontrolled artificial intelligence. In such scenarios, civilizations may self-destruct before reaching a level that allows for interstellar travel or contact with other species. Even if such civilizations existed in the past, they could have disappeared long before we began observing the sky. There are also more optimistic hypotheses. For example, highly advanced civilizations may simply not be interested in contacting us. If another intelligence's technology level is tens of thousands or millions of years ahead, humanity might be perceived as biologically primitive and insignificant, merely noise in the data. This could be similar to how modern humans don't interact with soil bacteria. In this hypothesis, we're neither destroyed nor intentionally ignored. We're just overlooked or deemed unworthy of attention. There could also be explanations related to differences in perception and thinking. We might search for intelligence based on our criteria, like radio signals and logical traces. However, another civilization might act in ways that don't register as artificial to us. For instance, its signals may be too fast or slow, or use transmission channels we can't detect, like neutrinos or gravitational waves. In such cases, contact could be possible, but occurs unnoticed, and we remain unaware. The Fermi paradox not only fails to provide definitive answers, but also expands the horizons of our understanding. It prompts us to rethink the criteria for life, development, and the sustainability of civilizations, along with our own role in the cosmic context. If credible evidence of extraterrestrial life is ever found, even in its simplest form, it'll be one of humanity's most significant events. The implications of this discovery will impact not just science, but culture, philosophy, technology, and our understanding of humanity's place in the universe. The scientific community will need to reassess its fundamental concepts. Biology, based on terrestrial samples, will gain a new object of study, possibly with different biochemical foundations, molecules, and evolutionary mechanisms. This will expand the boundaries of theory and practice, including medicine and bioengineering. Changes will also affect chemistry, especially in organic compounds, and the potential discovery of alternative biochemistries, like those based on methane or ammonia, will challenge current notions. The limits of organic synthesis and the sustainability of life will be reconsidered. Astronomy, in turn, will gain new benchmarks for searching for habitable planets and will update ideas about the formation of planetary systems, stars, and galaxies, considering the potential for life. However, perhaps the most significant changes will occur in cultural and philosophical realms. The question of our uniqueness is one of humanity's oldest. If life turns out to be the norm rather than the exception, it'll force us to reevaluate ourselves, our planet, and the future of civilization. Religious views will also need to be reconsidered, as existing traditions don't accommodate the concept of extraterrestrial life from theological, ethical, or historical perspectives. We might need to redefine humanity's place in the cosmos, where we no longer occupy a central position. There'll be a necessity for a new language of interaction, both literally and metaphorically. We'll have to answer questions like how to establish contact if it's possible, and what norms should govern interactions between different worlds, how to protect foreign life from accidental interference and ensure safety for ourselves. Even the mere anticipation of an answer changes our perception. We start to rethink what we have: nature, technology, and our planet's vulnerability. The search for life beyond the solar system becomes not just a scientific challenge, but also an ethical one, shaping an image of a future where humanity isn't at the pinnacle of existence, but merely part of a complex, uncharted universe. Thank you for listening to the lecture to the end. If you enjoyed it, subscribe, like, and share it with friends. Many exciting journeys through history, science, and space await us ahead. Until we meet again, may you always have a starry sky above you.